Have you ever seen a set of parametric equations and just thought, what in the world is that supposed to look like? We see the path, but what's the actual picture? Well, in this explainer, we're going to peel back that parameter, usually time, to reveal the hidden geometry. And to do it, we're going to build a toolkit. So let's start with a mystery. We've got our x and y coordinates, right? But they're both tied to this parameter t. Is the path they trace out a circle, a line, something totally different? This is the exact puzzle we're going to solve. And trust me, by the end of this, you'll be able to just look at equations like these and instantly see the shape.
And here's our game plan. First, we'll talk about why this is so important. Then, we'll build our toolkit with 3 really powerful techniques. After that, we'll put those tools into action. I'll show you a few common mistakes to avoid, and then we'll see how this all connects to something awesome, like building robots.
Okay, so why even bother with this? Well, parametric equations are amazing for describing motion. Where an object is at a specific time t, but if all you want to know is the shape of the road it's on, we need a rectangular equation, that good old y equals f of x format. It's kind of like trading a movie of a road trip for a simple, clear map of the route. Now, to make that switch from movie to map, we need the right tools. So we're going to put together a little toolkit with 3 different, really effective methods. Each one is designed for a specific kind of problem you're likely to run into.
Here they are, our 3 main tools. First up, direct substitution. This is your go-to when it's easy to get t by itself. Next, the Pythagorean identity. This is your secret weapon anytime you see sine and cosine. And finally, algebraic manipulation, a really slick shortcut for when you can just add or subtract the equations and make t vanish.
All right, enough theory. It's one thing to talk about tools, but it's another thing to actually use them. So let's get our hands dirty and solve a few problems. We're going to start with our most straightforward tool, direct substitution. Think of this one as the reliable workhorse of our toolkit.
So here's our first setup. X equals 3t minus 1 and y equals 2t plus 5. The big clue here? Notice how t is just t. It's not squared, it's not trapped inside a trig function. That's a huge sign that substitution is probably the way to go.
So first things first, let's grab that x equation and get t all by itself. We just add 1 to both sides. Then divide the whole thing by 3. And there we go. We've got a nice, clean expression for t.
And now for the magic trick. We take that whole chunk of stuff that equals t and we plug it right into the y equation, replacing the t that's there. And just like that, poof, the parameter is officially gone. Now we just have to clean up the algebra.
And after we simplify everything, we get this. Y equals 2/3 x plus 17/3. And what is that? You know this. It's the equation of a straight line. We've successfully turned a description of a path over time into a clear, simple shape. Okay, on to tool number 2. The second you see sine and cosine show up together in your equations, a little alarm should go off in your head. Ding, ding, ding! This is a job for the Pythagorean identity.
Hey, wait a minute. This looks familiar, doesn't it? This is our mystery problem from the very beginning. Now we actually have the right tool to crack it. X equals 5 cosine t, and y equals 3 sine t. So with this technique, the goal is a little different. We're not trying to isolate t. Nope, we want to isolate the entire trig function. So for the first equation, we'll divide by 5 to get cosine t all alone. And for the second, we'll divide by 3 to get sine t by itself.
And here is where it all comes together. We're going to bring in the most famous identity in all of trigonometry. Cosine squared plus sine squared always equals 1. It's a fundamental rule. So we can just take our expressions for cosine and sine and plug them right into that identity. When we square them, we get x squared over 25 plus y squared over 9 equals 1. Now, if you've been working on your conic sections, that form should be unmistakable. It's not a circle, it's an ellipse. And there you have it. Mystery solved. Okay, let's grab the last tool from our kit. This one is super clever. It almost feels like a shortcut. Instead of all that substitution, sometimes you can just add or subtract the 2 equations to make the parameter disappear. Take a look at this pair of equations. Now, trying to solve for t here would mean using a square root, and that can get messy. But notice that both equations have a t squared in them? That is a massive hint. So what happens if we just subtract that entire second equation from the first one? Well, on the left side, we get x minus y. On the right, we get t squared plus 1 minus the quantity t squared minus 1. And look at that.
The t-squared terms just cancel each other right out.
After the dust settles, we're left with x minus y equals 2. And if we just rearrange that to look a little more familiar, we get y equals x minus 2. Another straight line. How elegant is that?
So now we've got these really powerful tools in our hands. But like any good tool, you've got to know how to use them safely. Think of this part as the safety manual that comes with a toolkit.
There are two really common pitfalls you've got to watch out for. The first one is a big one, losing domain restrictions. Remember that last example where x was equal to t squared plus 1? Well, since t squared can never be negative, x can never be less than 1. That restriction doesn't just vanish when you eliminate t. You have to carry it over to your final answer. The second thing is misusing that trig identity. It's powerful for sure, but it only works if the angle inside is exactly the same. Sine squared of t plus cosine squared of t is fine, but sine squared of t plus cosine squared of 2t? Nope, that won't work.
At this point, you might be thinking, okay, cool trick, but when will I ever use this? Well, it turns out this isn't just some abstract math exercise. This exact skill is absolutely critical in fields like robotics.
Think about a robotic arm on a factory assembly line. Its path might be programmed parametrically, telling it exactly where to be at every single millisecond. But for the robot's computer to actually understand the overall shape of its path to make sure it doesn't crash into anything, it has to perform this exact conversion. It's literally translating its schedule into a map of its workspace.
So, we've done it. We've learned how to take a path defined by time and uncover the shape hidden beneath. We've built our toolkit and put it to work. But I want to leave you with one final question to think about. In this process of getting rid of t, what information did we lose? We gained the shape, the picture, but what did we have to give up to get it?